In your example, you're talking about a set of biomarkers about the aging process. So when we look at someone, we look at, let's say, the hair, the skin, the vision, the hearing, but we can also have some mental tests, how well people memorize things, how fast they solve some intellectual problems. So these are all biomarkers. But to my knowledge, there hasn't been a unified framework that links the development of biomarker values over time with observed mortality patterns. Demographers are looking at rates of aging from a much simpler perspective. Demographers work with life tables. And in a life table framework, one can reconstruct mortality rates. Demographers assume that mortality rates come from a data-generating mechanism described by a probability distribution with its hazard, or what demographers call force of mortality. When we deal with a life table, we talk about the rate of aging of populations. Then we have to make an additional assumption, which holds almost all the time, that populations are heterogeneous. They are constituted by individuals who follow different mortality patterns. In this line of thought, the individual rate of aging is just the relative derivative of an individual mortality pattern. Actually, not so much, because we can observe mortality patterns for populations. So these are our aggregated mortality data in life tables. But unfortunately, we are unable to see how individual mortality patterns develop. For a given individual, we have birth time, death time, maybe a history of diseases, but from these pieces of information, we are not able to reconstruct a mortality pattern, age-specific hazard rates. So we have to make a model. Human mortality in a given year or for a given cohort follows an S-shaped pattern. There is an initial exponential increase of adult mortality between ages 30 and 85 approximately, and then mortality starts decelerating, and there are some pieces of evidence that it actually levels off at the end. So the pattern is S-shaped. So following the model by Vopel, Menton and Staller at 1979, this pattern can result from exponentially increasing individual hazards given by the Gompertz function A times the exponential of bx, where x is age, A is the starting level of mortality at the initial adult age, and B actually is the rate of aging, because this is the relative derivative of the Gompertz function A e to the bx. So if individuals follow an exponentially increasing Gompertz patterns with the same B, the same rate of aging, but different starting levels of mortality, then the resulting pattern for the population is S-shaped. Is this the only model that can describe S-shaped patterns? The answer is no. There are numerous possibilities for individual hazards, not necessarily with the same rate of aging, whose composition, whose mixture yields at the end an S-shaped hazard for the entire population. But when one decides what model to choose, one has to think about the parameters of the model. Parametric models are designed in such a way that each parameter has a specific meaning, so that when this parameter is estimated, we can draw direct evidence about the underlying process. In this sense, the framework developed by Vopel and co-authors, the so-called frailty model, provides a convenient way to work with individual hazards. If we assume that within one population there are different subpopulations with the same rate of aging but different starting levels of mortality, what happens due to unhealthy behavior or some bad disease is that one jumps from one log mortality curve to a log mortality curve corresponding to a higher initial level of mortality but the same rate of aging. And there is evidence from data on patients who had heart attacks that at the age when they get their heart attack, the force of mortality rises immediately, but then within a year it starts increasing at the same pace as the force of mortality for the population that has not experienced a heart attack. So there are some pieces of evidence that basically the price that you pay for unhealthy behavior or some disease is that you just jump from one log mortality curve to a higher log mortality curve. But there is also a second possibility to look into this problem, and it is to estimate the individual rates of aging by cause of death. One has to be careful about that though, because mortality patterns by cause of death do not necessarily follow the mortality pattern for the overall mortality. And two famous examples are neoplasms. The force of mortality for cancer starts decelerating at age 55, much earlier, something like 35, 40 years earlier than the overall force of mortality. If we're talking about one and only one rate of aging for all cohorts, and this has been hypothesized by Jim Voppel in his article, The Biodemography of Human Aging in 2010 in Nature, this would mean that the individual rate of aging is a biological constant for humans. And this has several implications. Speaking about modeling, we estimate one parameter less, which is also helpful. Speaking qualitatively, mortality will depend just on the starting level of mortality at the initial age. And this is a cumulative effect of all genetic and environmental factors that contributed to this starting level of mortality. And again, we're talking about models that are fitted after age 30 at least. Mm-hmm. So we are talking about adult mortality. We're not taking into account accident-related young adult and adolescent mortality as well as infant mortality. So these are the implications. The number that I find very interesting is 0.02. This is the difference between the rates of aging, the individual rates of aging, for females and males. The individual rate of aging for females is on average about 0.02 higher than the rate of aging for males. Why is that unexpected? We all know that males have excess mortality in comparison to females, but still their rate of aging seems to be lower. So one explanation could be that the impact of a, colloquially speaking, accident-related mortality plays a much more important role for males than for females.